Okay, so like I mentioned, it's going to be kind of like the pre-chapter sort of lecture, and we're going to cover everything from measurements to significant figures. We're going to talk about some conversions and dimensional analysis and how to set up problems to make sure, again, everybody's on the same page. We'll hit some temperature conversions. And I am writing this just to remind myself maybe of what to cover. And maybe some density there that close it out, I think maybe. We'll see. All right. So once again, in your book, it is comes before chapter 1. I think it's called like a review chapter. And like I said, you will be obviously responsible for this information, be able to give your answers and stuff like that to proper number of significant figures. Also be able to obviously set up problems to show your work properly using dimensional analysis. And like I said, it will be a part of exam 2. There'll be some questions on it from there. All right, so let's just start with really measurements and units. So whenever you take a measurement, which is a quantitative type of observation, there's really qualitative, and qualitative observations are really just that, things like, it turned a certain color, there was sort of steam that came off or gas that came off. Quantitative usually involves a measurement, and when we take measurements, it's always important to have two things. So for example, if I wrote 155, what am I talking about? 155? Who knows, right? It's just a number. Could be $155, which would be great. 155 pennies, still not bad, I suppose. Could be 155 apples, could be good as well if you like apples, I suppose. But a number by itself obviously is useless if it doesn't have a unit associated with it. So whenever you give any type of measurements, you should always have a number, and you should have some type of unit, which obviously gives whoever's looking at it a idea of what the number represents, maybe it's centimeters or something of that nature. So units are really important, and as you may be familiar with, there's kind of like two categories of units that are oftentimes used. There's the English units, which is sometimes also called the US sort of units. And there's pretty much what everybody else uses in the world, which is metric. And so there's kind of the English and the metric sort of system. And as you may know, that as obviously the world got smaller and people sort of do business and stuff with each other, having different types of units is not so great, right? If somebody's doing on the English sort of system, somebody's rolling with the metric, there's going to be some problems with that. So the result of that was, and as you may be familiar with, somewhere around 1960, they had a conference of weights and measures, and they really came up with a international system of units, which you oftentimes hear in chemistry, which is sometimes referred to as the SI units, and that's the international system of units. Truth be told, it's really the metric system that kind of won out there. And it's really based off of the metric system. So a lot of times in chemistry, you'll see like the SI unit is this, or the SI unit for that is something else. It's also really important when you look at units that you do understand what they represent. So if you had something like a kilogram, that does represent a mass, right? So that's not a volume or anything like that. If you had something like a liter, that is a volume, right? Not a mass. And I can't tell you how many people has told me that the volume of their solution is 400 grams, right? So, or the mass of their solution is 500 milliliters or something like that. So you do want to make sure that you do have an understanding, obviously, of what these things represent. Like the meter is a length, right? Kelvin is a temperature value, right? Um, so you want to make sure that you truly understand those type of things. When we look at units and when we look at sort of the metric system, we oftentimes will use prefixes, right, to sort of change the value of it. And a lot of times people, when they look at something like kilo is 10 to the 3. They'll look it up in a table, such as like something I got here, right? Got all these sort of values and stuff like that. So it's very common when people sort of see these sort of values that they don't necessarily use them correctly in sort of a conversion or something like that. They oftentimes will use it sort of backwards and stuff like that. Our nano is 10 to the minus 9, for example. So when we look at these things, what that represents when you sort of see these things is that is how much there is in the base unit to one of the prefix units. So what I mean by that is if we were, for example, trying to go from, say, our maybe kilograms and grams, right? So the base unit in both of these here is really grams. It's the base unit. That is really the prefix unit. So if you were go to your table and look up kilo and see 10 to the 3, what that means is in one of the prefix units, the kilograms, there is 10 to the 3 grams. And it's very common. People always sort of do that one backwards. They'll do like 10 to the 3 kilograms is 1 gram and stuff like that. Same thing here with nano. If you had like nanometers and meters, again, the base unit here is meters. And if you go to the table and look it up and find 10 to the minus 9, what that would mean is 1 nanometer, there are 10 to the minus 9 meters. So again, that is the proper way to do these. These are what are sometimes referred to, right, as equalities, right? And equalities are basically two things that are on different units, but they represent the same amount of something, right? Like if you had 100 pennies, it's the same as $1, right? So they represent the same amount of money, but they're on different units. So you do want to make sure that if you go to that sort of prefix table or use that prefix table, that you do use the conversion sort of correctly. That's a super very common error that people make is they always sort of kind of reverse those things. So by the way, from any equality, right, you could write conversion factors, which are basically just fractions that you could use in calculations, which we'll talk a little bit about a little later on, 1 nanometer over 10 to the minus 9 meters, or you could do the opposite, 10 to the minus 9 meters over 1 nanometer. By the way, the 10 to the minus 9 or the 10 to the 3, that is basically scientific notation. That is basically 1 times 10 to the minus 9 or 1 times 10 to the 3 is basically what those represent. Any questions on that? So I would say in chemistry a lot, we do use really the SI system, which is really a lot of times we do use the metric system a lot, and we do use these prefixes a lot to change it. We do interact and kind of cross over to the English system and use some of those units a lot as well, like pounds and stuff like that. Grams to pounds is very common as well. So speaking of measurements, when we give a measurement, we always want to make sure number and unit is always associated with them. When we do take a measurement, there's always some degree of uncertainty. So no matter what type of measurement that you take, there's always going to be some degree of uncertainty with that measurement. The degree of uncertainty with that measurement is based on really the equipment that you're using to take that measurement. So for example, if we just take something like this, and we make like a little ruler action happening here, we'll call these centimeters. And let's just say we wanted to measure my arrow here. We'll go right about there. And we have this ruler. And whenever you take a measurement, it's really important to do really two things. And when you look at the scale, and that's why they put the scale on these things, is for you to look at them. You want to figure out two parts to it. And usually there is sort of a large marking, and there's usually a small marking. Now, the large markings usually will have numbers. So in this case, our large marking here represents 1 centimeter. Now, the smaller markings are represented by all the dashes, whatever they may be, in between the two larger markings. Now, when we count them up, we always want to count starting with the first marking past the last large marking. So what I mean by that is we would start counting here. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we would stop at the large marking. So in this particular case, we have 10 small markings between a total sort of distance there of 1 centimeter. So basically, if you take 1 divided by 10, each of the small markings represents 0.1 of a centimeter, right? So that is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then obviously over there to our 2. So when you do take a measurement, those are really the two things that you always want to sort of look at and try to figure out. And that's going to help you take a proper reading. And let's talk about taking a proper reading. So whenever you take a reading, no matter who looks at it, there should always be certain numbers that everybody should agree upon. So if we look at my arrow here, no matter who looks at it, everybody should agree it is at least 1.3, right? And we would record those numbers, and those are sometimes referred to as all the certain numbers. Now, clearly, when not exactly 1.3, and it's not exactly 1.4. It is somewhere in the middle-ish of that. And that is where really the uncertainty comes into this measurement. That is really where the estimation comes into this measurement. We need to look at it and try to decide that. In this particular case, maybe you look at it and go, it's about halfway between it. And maybe you record a 5 as that last digit, and obviously our units with it. This would be what is referred to sometimes as the first uncertain number. Now, it's uncertain because somebody else may look at it and go, I think it's a little closer maybe to the 1.4, maybe it's like 6, maybe somebody else says that's a little less than half, maybe it's 4. So usually when you take a measurement, it's like plus or minus 1 of that last uncertain digit that you put there. And in this case, when we do this, the importance of taking a measurement like this is when you take all the certain numbers in a measurement and the first uncertain number in a measurement, that is pretty much what significant figures are. That would mean that this measurement here has 3 significant figures, right? There would all be significant, with the uncertain number there being in the last digit, which is our 5. Any questions on that there? Now, if you had something, say like a graduated cylinder, say these are milliliters, we'll put a liquid in there. So when we want to go measure this liquid in this particular graduated cylinder, and whenever we put a liquid in a glass cylinder, we typically will see dramatically drawn here the curvature of the liquid, and that's what's known as the meniscus, right? And we always read, in most cases, from the bottom of the meniscus. This occurs because the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. So what happens on the sides where it hits the glass, it starts to rise up the glass through capillary action, and because it's attracted stronger to the glass, and that gives you that traditional U-type shape, which is what a meniscus usually looks like. By the way, not all meniscus will look like that. There are certain chemicals that are elements that actually will do a meniscus that looks in the opposite direction. We don't see it too much because they've taken mercury out of most labs, but mercury will actually go the opposite way. It will actually do an inverse sort of meniscus. In that case, you would actually read from the top of the meniscus. But I would say in your case, most of the time they will look in the U fashion. We read from the bottom of the meniscus because if there wasn't that attractive force that brought the liquid up, it would be back down where the middle is, right? Where it's not in contact. So that's why we take the reading from the bottom of the meniscus. So we still want to do really the same thing here. We want to look at our large scale, which in this case here, our large markings are going to be 10 milliliters. Once again, we want to count up how many small markings there are between. So starting after that last large marking, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, here we have 10 small markings. 10 divided by 10 is going to be 1 milliliter is what each of these represents. So that guy there would be 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Now, when I look at my bottom of my meniscus, which is so much drawn right there, we could clearly see here that everybody should agree it is at least 14. But again, we're not exactly at 14, not exactly at 15. In this case, maybe it looks a little higher, right, than halfway there. So maybe you go with like a 7 milliliters, right? This would be all my certain numbers. This would be my uncertain number. And once again, this guy would have how many significant figures? Would have 3 significant figures once again in here, with the 7 being the uncertain number. Any questions on that there? Now, it is important to look at your scales because you may be using the same equipment as your neighbor. They may both be 10 milliliter graduated cylinders, but the markings may be different. So for example, if I had this graduated cylinder here, we do a little something like that. Once again, if we look at the large markings here, our large markings is going to be 10 milliliters. If we count up what we got going on in between, 1, 2, 3, 4, and only 5 in this case, that means that each of the smallest markings represents how much? 2 milliliters, right? 10 divided by 5 is 2. That would mean that is 12, 14, 16, 18, 20. So now when we go to take this reading, we're somewhere here-ish. Between 14 and 16 is which number? What comes between 14 and 16? Yeah, it's not a trick question. It's 15, right? Milliliters. And in this particular case, that is really the best that you could do. And that is because there's not enough room between 14 and 16 to know exactly where 14 ends and like where 15 starts, right? And ends and all that. So you can't really do any better than that. By the way, this would then have how many significant figures? Would have 2 significant figures. The uncertain number here would be the 5. Yeah, so that's our uncertain number, our estimated number. That would be our certain number. So it does depend on the piece of equipment, it does depend on the markings as to how far you should take a reading to. You should always take a proper reading and you should always look at your scaling when you record measurements. So things should not just be whole numbers all the time. There should be some decimals on measurements and stuff that you make. By the way, when you use something that is digital, should you record all the numbers or just some of them? You should record all the numbers on something that's digital. The numbers would not be there if they weren't important. So when you use something like the balances, which we'll use at some point, I imagine, you should always record all those numbers. So when you go over there and it says 56.256, that's what you should record, not like 56. Yeah. And the reason for that is it's really important not to mess up your measurements. So for example, if we went back, say, I'll make another one here. Let's just say we had kind of a similar situation to what we had earlier. And we have this ruler here. And let's say my arrow in this case was like right on that line. And again, we've already looked at this guy. We have our large marking, which is 1 centimeter. We have our small marking, which is 0.1 centimeters. And we can see 1.1, 1.2, 1.3. So when I take this measurement, should I record 1.3 centimeters, 1.30 centimeters, 1.30000000 centimeters? I feel like that's too many, and I would agree, too many zeros. More is not always better in some cases, yes, so that is definitely not right. Is there a difference in terms of which one I record? There is a difference. So just to illustrate that difference, let's just say, for example, we took this one here, and this is the one that we wanted to record. How many significant figures does that one have? Has 2 significant figures. So what you're saying in this particular case is, I think the measurement is 1.3, but maybe it's like 1.4, maybe it's like 1.2, which is clearly a very big realm of sort of error, right? That's that whole area there. It's somewhere in that ballpark, which clearly it doesn't look like that, right? If we look over here, this one would have how many significant figures? It would have 3 significant figures, as these would be our certain and our first uncertain number there, right there. That means that when you say, I think it's 1.30, you might be saying, I think it's 1.31, or maybe it's like 1.29, which clearly is in that area, which is obviously based on the scaling there, what we do see in our measurement. So when you lop off a number and a measurement that should be there, you're actually making your measurement a lot crappier. Yeah. So this is not the right one. This is the one we should do it with, because on this particular scale, we have the ability to go to that many places. Typically speaking, you have the ability to go one more place to the right of the smallest marking. Not in all cases, but in most cases, you have the ability to go one more place to the right than the smallest marking. As you can see here on the guy on the left, you don't have that ability. Now, if you want to know how far you can really take a measurement and you're maybe not sure how far you should take the measurement, but you could still figure out, the smallest markings, what they represent, all you have to do is essentially just divide the smallest marking by 2. That is 1 milliliter. That's how far you should take the reading to. You take the smallest marking here, which is 1 milliliter, divided by 2. That is 0.05, which is 2 decimal places. I'm sorry, it's 0.5. There we go. 0.5, which is 1 decimal place, which is how far you should take the reading. Over here, the smallest marking is divided by 2. That is my 0.05. That is 2 decimal places, and that is how far you can take the reading. So if you divide the smallest marking by 2, it'll give you like a 0.5 number, 0.05 in a lot of cases. That'll tell you how far you can take the reading if you're not sure. But the general rule is you can take the reading one more place to the right of the smallest marking. Any questions on that there? So clearly you do need to take a proper reading. Anytime you take a reading, there are better pieces of equipment to take readings than others. So for example, if I had a beaker, if I had a graduated cylinder, or between the two of them, which one would be a better one to use to take a reading? The graduated cylinder should be a lot better. If you ever look at a beaker, they typically have just very few markings, right? This has a lot more markings typically, so you should use that. By the way, this also has a much larger opening, right, than say this, which means when you find the meniscus in here and you think you filled it up to that 50 mil line, you're going to be nowhere near the 50 mil line because of the spread out of the meniscus. It will appear like you put it up there to 50, but it'll be nowhere near it. So much better to use the proper equipment. just like a beaker would be a terrible thing to use to measure out and transfer a certain volume of liquid. Something like a pipette would be a much better thing, or a burette will be a much better thing to use to transfer liquid as well. So you want to make sure you also use the proper sort of equipment when you are transferring liquids as well, or measuring out liquids as well. Flask, also a very bad thing to measure out a volume, unless it's a volumetric flask, which is a really good thing to measure out volume. Volumetric flasks typically will have only one marking, and that's a pretty accurate thing. If you fill it up to that marking, it will represent basically the right amount. Anything that's volumetric, volumetric pipettes, they have kind of like the little bubble that comes out. Also will typically have one marking. Volumetric means expensive, don't break it, but it has one marking. If you ever use anything that's volumetric that has just one marking on it, typically speaking, you usually take the measurement to 2 decimal places is typically what you would do. So if this was like a 100 milliliter volumetric flask, you would record the volume as 100 milliliters. If this was like a 10 milliliter volumetric pipette, you would use 10 milliliters with 2 decimal places. So typically speaking, if anything's volumetric, which basically has usually one line, and that when you fill it to the line is the total volume. Very good thing to use for measurements and transferring liquids, but typically 2 decimal places. Now, when we talk about sort of measurements and stuff like that, there is sort of accuracy, right? And precision. And there is a difference between accuracy and precision. Accuracy is how close you are to the true value. Precision is how close a set of numbers are to one another. So the classic example is like if you threw darts at a dartboard, right? And if I throw my darts and I hit a dart here, I hit a dart there, maybe I put a dart there. Am I very precise? Am I very accurate? I am not, right. The goal is to get the bullseye there in the center. So not so good there, but that's why they invented double or nothing, right? So you go double or nothing, right? You pick up your darts, you have a little bit more confidence, you're warmed up now, and you throw them. Am I precise? I am. Am I accurate? I am precisely not accurate, right? So it brings up a good point that you can be very precise, but you could also be very inaccurate, which means you could do the exact same thing the same way every single time. But if you're doing it wrong every single time, you're going to end up wrong every single time. But you'll be very precise in how well you're doing it because you're just repeating the same steps. Typically with precision, right, it's why we do a lot of multiple trials for something, right, to see if something's reproducible and repeatable. Why we do, say, 3 trials of an experiment or 4 trials of an experiment to see if you can repeat it. Now, I take my darts and I got a little better. I hit the board at least. So we're going to go triple or nothing, right? So I go triple or nothing and I throw my darts. Am I precise? Am I accurate? I probably hustled you as well, but yes, I am precise and accurate here. And that really is the goal when you do experiments, right? You want to be accurate to get the right answer to what the true value is. You also want to do it in a way that's very precise as well and reproducible, that you could continue to do the same procedure over and over again and come up with the same result, right? You know, you can't really prove something if you do it once and get lucky and it just happens once, right? And you do it like 400 times and it never happens again, right? So you can't really do that. But if you're able to do some type of experiment where it's very consistent, that you get the same results, you get close to the true values, you know, that's really what we're looking for. When we look at accuracy, a lot of times we look at what's sometimes referred to as percent error. And to calculate percent error, you can take your experimental value minus your true value divided by the true value, and you can times it by 100%. Now in this class, they oftentimes will have you just do the absolute value of it. You don't necessarily have to do it. You could get a positive number or a negative number for percent error. It just means negative, you missed it on the low side. Positive, you missed it on the high side in terms of the true value. Precision, we sometimes look at a little standard deviation, right? A little their square root of your value minus the average squared and the sum of that divided by n minus 1. And sometimes we look at percent standard deviation, which is basically your standard deviation divided by your average times 100%. And these are some things that we sometimes look at in terms of precision and when we do multiple trials to see, again, how reproducible they are. In this class, we pretty much will just use percent error most of the time. We won't use too much standard deviations and stuff like that in this particular class. Any questions on that there? Now, speaking about significant figures, let's talk about, again, just the rules again to remind everybody how to assign them. So the first rule is any non-zero is significant. And we always count left to right. So when you're counting significant figures, you should always go left to right and start counting once you hit the first non-zero number. So in this case, they're all non-zero, which means this guy would have 3 significant figures. Second ones are zeros, and there's different types of zeros. So the first type of zero is what is sometimes referred to as the leading zero. And they are not significant. So if you had 0.00023, we would go left to right. None of these would be significant. We would not start counting until we hit the first 2 there, which is a non-zero. The 3 is also a non-zero. This would have 2 significant figures in this particular case. There's also sometimes called captive zeros, trap zeros, whatever you want to call it. They are significant. And those are zeros that are between 2 non-zero numbers. So starting to count here, these 2 zeros would be significant. That would be significant as well. This would have 4 significant figures in this particular case. Lastly, probably the zero that gives people the hardest time is the 0 at the end. And that's sometimes referred to as the trailing zero. And they may or may not be significant. What makes a trailing zero significant is they will be significant if there is a decimal point in the number. The decimal point does not need to be near the zeros. It just needs to be anywhere in the number for them to be significant. So if I had 400 written like this, it would have how many significant figures? Would have just one significant figure, which would be the 4 in front. The zeros in the back, not so significant. If I wrote 400 like this, how many significant figures would it have? Would now have 4 significant figures. Decimal point makes all these zeros significant. We would start counting at the 4 in this case. Now, when we look at some number like this, 0.00010030430, if this was some weird measurement, how many significant figures would this be? I'll trust you. I just started writing numbers. So let me see here. So we start left to right here. We're going to go this way. Those are all going to be not significant because they have not hit the very first non-zero. And that's where we should start counting. So that's significant. These 2 are trapped. Those are significant. 3 significant. Some more trapped are significant. These guys are significant. So that's 1, 2, 3, 4, 5, 6, 7, 8. Now we have the 3 zeros at the end. Are they significant? They are significant because way over here, there is a decimal point, which would make them significant. And again, I think you said 11, which I think I agree there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 in this case. So again, sometimes people think the decimal needs to be like right next to the zeros. They don't have to be. They could be anywhere in the number. Yeah.
If you want to write 400 2 significant figures, you do 40 times 10 to the 1.
You wouldn't do 40 times 10 to the 1, but you have the right idea. You would have to write in scientific notation. And we'll talk. Yeah, so yeah, we'll talk about that in just a second. But yeah, that would be the only way. And there is sometimes only one way to write a number with the proper number of significant figures, which would be to write it in scientific notation. So the reason I said you wouldn't do 40 times 10 to the 1 is that's not really proper scientific notation. And it does has to be a number between 1 and 10. So this first guy does need to be a number between 1 and 10, not 10, but it's got to be between 1 and 10. So that would be the right way. But yeah, you would have to kind of do that in that case, which is why, for example, if we had something like 12,000, right? And we did want like, say, 3 significant figures, there's really no way to do that, right? There's no way to get me to 3 significant figures without writing a scientific notation. So question on that there. Okay, so more importantly, though, when we do calculations with scientific notation, right? Not scientific notation, calculations with significant figures. There's basically 2 kind of sets of calculations that we do. We either will add and subtract, or we will multiply and divide. Or divide, I guess, and or, I guess, further. And we'll start with the multiplying and dividing. If we multiply or divide, or both, the answer should have the same number of significant figures as the number with the least number of significant figures. So for example, if I took 4.50 and I multiplied it by 1.2, here we are multiplying, we would look at significant figures. That is going to be 3 significant figures. That's going to be 2 significant figures. So when we do get our answer, we should end up with 2 significant figures as our answer based off of that calculation. So again, same thing, if you were dividing something, whichever number in that sort of division or multiplication is the least number of significant figures, that is technically how many significant figures your answer should have. When we add and subtract, we're actually looking at decimal places and not significant figures. So our answer should have the same number of decimal places as the number with the least number of decimal places. So if I took 1.220 and I added it to 2.4 and added it to 3.21, we'll give it the old college try here without a calculator. 3, 4, 6, 8, 5, and 6 in this case. So when we're looking at this, we're going to look at decimal places. So this has 3 decimal places. This has 1 decimal place. This has 2 decimal places. So in this case, our answer should actually go to 1 decimal place, which would give us 6.8. 6.8 has 1 decimal place, but how many significant figures? It has 2 significant figures, right? And that's important because sometimes you do all these things together, right? Sometimes you might add and subtract and multiply and divide and kind of mix and match things. So when you are doing calculations where you're doing maybe multiple steps together, you do want to keep track of your significant figures and where your answer should end up. So if you had something like, 32 times 1.11 times 4.256 and divided it by 123. In this particular case, the first thing we would technically do is the top part in parentheses. And in this case, we're multiplying. So we're going to be looking at significant figures. This has 2 significant figures. This has 3 significant figures. That has 4 significant figures, which means technically when we get an answer up on top, it should have 2 significant figures up on top. On the bottom, it has 3 significant figures. So the next thing we're going to do is take 2 significant figures divided by 3 significant figures. which means we should end up with our answer having only two significant figures in this case. Now, this brings up another really important thing, which is I would not round until the very end. So I would keep track of your answers. If I did the top part of this calculation, I would take the whole number of my calculator and just continue on with the calculation. I wouldn't round too much. If you round a little bit along the way, every time you're kind of doing multiple calculations and steps, you will kind of move yourself further and further away from the right answer because you're kind of reducing down the number of numbers. So I personally wouldn't round. I would keep the number, take it to a few extra digits that you don't need. And then at the end, you could clean it up to the right number of significant figures. Sometimes people are taught to keep a couple, they call it guard digits, I think, put a little line over something, of the ones you're keeping. But, you just want to keep a few digits and not go too far. And that also includes, something if you were even crossing over, say, you did 1.2 times 3.33, then we're going to add it to, 14.1 or something like that. So here we would get an answer, for example, and we would get like 1.2 times 3.33 on our calculator spits out 3.996. At that point, we would then go to 14.1. At this point, technically speaking, if we were to sort of stop our answer with just this part, we have two significant figures and three significant figures, which means we really should go there, right? And technically that should round to 4.0, not just 4, by the way. So that should round to 4.0. But we could then add both of these numbers together and we could take 14.1 and we will end up with 18.096 on your calculator. So technically we should go here, which is two significant figures. The last thing we're doing is adding. So we would look at decimal places. They actually would both technically have one decimal place, which means our answer should end up at 18.1 over here, which has one decimal place, obviously, in that case. So you really do want to sort of end it with your last calculation that you did, but you do have to kind of keep track of the numbers going through those calculations to know where to properly maybe round a number to and stuff like that. Any questions on calculations with significant figures? Speaking of rounding, normal rounding rules apply, right? If it's above 5, we round up, right? Less than 5, we kind of just drop off the numbers and stuff like that. You don't want to do anything crazy, right? So if you have, say, 13,333 and you want two significant figures, what should the answer be in this case? 13,000. So when we look at this has two significant figures, right? I wrote this way. This has two significant figures. They both have two significant figures, right? Now, whenever you round, you never ever want to change the meaning of the number, right? So there's a very big difference between 13 and 13,333. Like if I owed you $13,333 and I said, I'm going to pay you two significant figures, here's 13 bucks. I'm probably not going to make it out the door. Maybe I will. You look like nice guys. But if I give you 13 grand, maybe I get the, $333 teacher discount or whatever it may be there. And, it's basically the same value. So although they both have two significant figures, this would be the proper way to do it. You could also use scientific notation as well. But to maintain the value of the number. And that happens a lot, especially when people are trying to get the right number of significant figures. They go a little extreme rounding, and you never want to change the meaning of the number when you do that. Any questions on that there? Now, speaking of scientific notation, as we talked about, that is oftentimes a way that we handle very large and very small numbers. And it does have a general form of n times 10 to the n, this being a number again between 1 and 10, this being either a positive or negative value. And it's really depending on which way you need to move the decimal place to get it to a number between 1 and 10. So if we had 100 or 1, 2, 3, 4, and we wanted to put it in scientific notation, we would go assume the decimal points there and go 1, 2, and 3 places to the left. 1.234 times 10 to the 3 would be the proper way to write scientific notation in this case. We have something like 0.00400. And in this case, I want to get it to a number between 1 and 10. I got to go one place to the right, 2 places, and 3 places to the right. That will give me 4.00 times 10 to the minus 3. Typically speaking, if you move the decimal place to the right and you have the number in positional notation, that will give you a positive exponent. If you move the decimal place to the left, you'll have a negative exponent. Or if you want to remember it this way, large numbers above 1 have a positive exponent, smaller numbers have a negative exponent. Whenever you write a number in scientific notation, all the numbers that come before the times 10 part, so all these numbers here, they are always significant. So that means when I write this number in scientific notation like this number will have 4 significant figures, which matches, by the way, the 4 significant figures the number originally had. You never want to lose any significant figures along the way. That is also why over here, how many significant figures does this one have? It does have 3 starting at the 4, and those 2 are significant because there's a decimal point in the number. That has 3 significant figures. Written like this also has 3 significant figures. That is why I did not drop the zeros in this case, because if I dropped the zeros and wrote it like this, how many significant figures would it have? It would have just 1, yeah? So whenever you write a number in scientific notation, the numbers that come before the times 10 part are always significant. And that is why I said earlier, for example, if you had something like 12,000, there's no way to write it in sort of a decimal form to get yourself to 3 significant figures if we wanted 3 significant figures. Again, if you did something like this, that's 120, which is 3 significant figures, but once again, does not mean the same thing as 12,000, so that would be incorrect. But if you did 1.20 times 10 to the 1, 2, 3, 4, that will now have 3 significant figures and the proper way of writing that. The beauty of scientific notation is if you needed 4 significant figures, you frankly could just add a 0. And now I have 4, right? If I needed just 2, drop a 0. And now I have 2 significant figures. So scientific notation gives you the ability to give any number really to whatever number of decimal places or whatever number of significant figures that you need by adjusting it. Any questions on scientific notation there? Now, more important in scientific notation, which is scientific notation and your calculator, yeah? And most people don't know how to use their calculator with scientific notation and your calculator. So let's talk about how to properly punch these numbers in, which will make your life much easier, especially around experiment 2, stuff like that. So on every calculator that there is, there pretty much should actually be and was referred to as an exponent button. On some calculators, that's an EE button. Other calculators, and it's an EXP button. And some of the newer sort of calculators will have actually a 10 to the n button. And usually those calculators will also have like a little wheel action happening. So if you have any of those, if you have that button, we'll talk about that in just a second, or if you have one of those two, I would say those are 3 of the most common exponent buttons. There's a 4th one I just saw recently, but most calculators will have one of these 3 here. Also, there is actually a negative button, if you will. And that on most calculators is this button, or this button is not the subtract button, by the way. So when you go to punch something into your calculator in scientific notation, you want to make sure that you're actually punching it in correctly so that you do get the right answer. So if I had something like 1.25 times 10 to the minus 4, and I wanted to properly punch that into my calculator, this is what you should do. We'll start with these buttons here. you should hit 1.25. You then should hit your exponent button, one of those two buttons. And on your calculator, it will either do one of two things. It will probably go 1.25. It may just pop an E up next to it. It may also do 1.25 and maybe pop up a couple of zeros, or it may even like throw a little times 10 very small and pop up a couple of zeros, something like that. When you hit that exponent button, that represents the times 10 part of the number, which means at no point when you're putting a number in scientific notation into your calculator, should you hit the multiplication button, should you do like the shift log button, unless you like wrong answers. You should not do any of those things. You should just hit that exponent button. At this point, what's left to punch in is the -4. Once again, do not use the subtract button. Use your negative button. And that will make this a negative. That will pop a negative in there. And then you hit 4. And that'll be a 4. This will then change to a 4. And that is the proper way to punch a number into your calculator in scientific notation to get the correct answer. And now, if you do have this sort of setup, and in my experience, if you have this calculator, it's not a big deal. And usually they're oftentimes two-tone, like they have a main color and like the sides are different colors and stuff like that. You just have to actually put a lot of parentheses into your calculation to make sure that your calculator actually does the right sort of calculation. So if you have this type of setup, you would actually start with the parentheses. You would actually type in 1.25. You then would hit your exponent button. And what it will look like most likely on your screen is this. You'll have a parentheses, you'll have a 1.25. It'll actually put the times 10. And then you'll have like a little cursor blinking up on top. And when you have this little cursor blinking up on top, at this point, you could then do the rest of it, which is just like the other, hit your negative button and then hit 4. And that will then turn this into 1.25 times 10 to the -4. Your little cursor will move to the right of the -4. The problem is on most calculators like this, your cursor is still up on top, which means it's not going to be happy with you if you just close the parentheses, because you'll get a small little parentheses up on top and it will not work right. So that's where the little dial comes in. At this point, what you actually want to do is take your dial and press this button over there. And what that will do is drop your cursor back down to normal size. And you will now look like this with a regular size cursor. And finally, you could close the parentheses and it will look something like this. So, although I did it step by step, it doesn't take all day to do it. But if you do have that type of calculator, you definitely have to put parentheses around every number that you put in scientific notation. Otherwise, your calculator will do some weird math and stuff like that. If you have the EE button, the EXP button, you don't have to be that careful. You pretty much can just hit the button and don't worry about parentheses. You'll be okay. But if you definitely have that set up, you definitely have to do that. Any questions on that? So make sure that you know where your exponent button is. Why don't we just try a couple here just to make sure everybody knows how to punch them in. Let's do 1.25 times 10 to the minus 3 divided by 4.2 times 10 to the 22. And then let's do 3.2 times 10 to the minus 6 times. And if I was to punch this in, I would go 1.25. I would hit my exponent button. I would then hit my negative button and 3. That would take care of this number. I would then hit my divide button and punch this guy in the same way, 4.2. Exponent button. This is a positive exponent, which means you don't need the negative here. So that would punch it in for that, hit equals. And if you do all that good stuff there on your calculator, you can end up with 2.976190048 E minus 26. So this is what it looks like in my screen there. So a couple of reminders. Obviously, your calculator does not give you your answer in proper scientific notation or significant figures. Or significant figures, I guess is a better way of putting that. By the way, here I'm dividing, which means how many significant figures should I have? Should have 2. This has 3 significant figures, right? And this has 2. which means my answer should have two significant figures, which does take me to here, right? That means I do need to look at the 7, which means I should round up. And this actually should be 3.0, right? Now, the reason I wrote it like this is very common. People forget this part of it. And that does represent the times 10 part. So you do need to write times 10. By the way, you should not write E when you're giving the answer. You should write times 10. Yeah. And that is the exponent part to the minus 26. Yeah. So it's very common on some calculators. It will look like this. By the way, on some people's calculators, screens will have that front number, whatever that number was there, 976190448. And they'll just have like minus 26, like way up high. It's very common. People will sort of forget this part of the number when they're given the answer. So remember to make sure that you do include that part of the number when you're given the answer. Any questions on that? Now, if you find yourself close to the answer, but your exponent part's off, it is probably the way you're punching into your calculator. That's usually a pretty good sign. If the front number looks good, but the exponent part's off, it's probably the way that you're punching into your calculator. Same thing here. We're going to go 3.2. Once again, going to hit the exponent button. Going to go with the negative button in 6, which will take care of that guy. Going to hit the multiplication button, 1.6, exponent button, and positive 9, hit the equals. And in this case here, 3.2, negative 6 times 1.6 to the 9. Going to give me a 5120 on my screen. I should end up with what in terms of significant figures on this one? Should be 2. These are both scientific notation. They both have 2 significant figures, which takes me to here, which means I should really have 5100. Should I put a decimal point? I shouldn't, because then that would be 4 significant figures, right? Or you could do scientific notation 5.1 times 10 to the 123. Should I put any zeros after the 1 here? Again, you wouldn't, because that would be 2 significant figures in this case. Any questions on that? So that is really where a lot of people struggle, is like punching in numbers in scientific notation into their calculator. Always use the exponent button. Never use like the shift and log button, or the 10 and the caret, or the multiplication, because you will find yourself really off. And later on in chemistry life, when you do things with logs, you'll find yourself even further off if you're not using the proper scientific notation. So it's really important to make sure that you know how to punch that in properly. Again, if you're not sure still, just come find me. We'll find it on your calculator as to how to properly punch it in, and make sure you know how to do that. Any questions on scientific notation? Okay, we're going to take like a 10-minute break, stretch our legs, and we're going to continue on with the last. Okay, we're going to continue on here and talk about a few other things that were in this review chapter. Any questions on anything that we've talked about so far? Everything all right? Yeah. So we finished talking there about scientific notation, as I mentioned before. Again, if you still are not sure how to properly do that on your calculator, just bring your calculator up and we'll figure it out together. The next thing we're going to talk about is temperature conversions and the different sort of temperature scales that we come across. So in chemistry, we really come across 3 different scales. There's degrees Fahrenheit, degrees Celsius, and Kelvin. And the major difference between these 3, at least with Kelvin, for example, is it is not degrees Kelvin, it is just Kelvin. Kelvin is sometimes also referred to as the absolute temperature scale. And there is sort of conversions between these different sort of temperature scales. I would say most of the time, we're oftentimes given temperature values in Celsius, degrees Celsius. That's a common unit that we are given values in. And I would say probably 99 times out of 100 in chemistry, you will be taking that Celsius to Kelvin as a conversion. So to do that, if we wanted to go from Celsius to Kelvin, temperature in Kelvin is equal to the temperature in Celsius plus a 273. The proper number is 273.15. Most people leave the 0.15 off since it gets rounded off a lot of times anyways. If you want to leave the 0.15, you can. But personally, I just roll with the 273 is okay. That also means, though, that if we do have a number in Kelvin and one Celsius, we're going to basically just subtract the 273. So we'll subtract 273 there, and that will take us back to Celsius. I would say probably, like I said, 99 times out of 100, those are the two that you're going to use most in chemistry. Fahrenheit, not seeing a lot of problems, but it does pop up occasionally and stuff like that. But Celsius, really going Celsius to Kelvin's done a lot, and Kelvin back to Celsius also as well. In this case, if we did want the temperature in Fahrenheit, that equals 1.8 times the temperature in Celsius plus a 32. And if you have the temperature in Fahrenheit and you want it in Celsius, the temperature in Celsius would equal temperature in Fahrenheit minus 32 divided by 1.8. That 1.8 is also the same thing as 9/5, the fraction that maybe you learned as well. Some people use 1.80. Now, when we're doing some type of temperature to temperature conversion and essentially just converting the temperature value from one unit to the next in terms of temperature, we do follow a slightly different significant figure sort of rule. So for example, I don't know if we had 41 degrees Celsius and we want to know what is the degrees of Fahrenheit, we would pop that into our equation. And if we do that on our calculator there, we will end up with 105.8 degrees Fahrenheit. Now, the general rule that most people follow when they're doing, like I said, just temperature to temperature conversions is we typically will make the converted temperature value look like the original temperature value. So what that means is this guy is pretty much a whole number. So we would actually take this guy to a whole number. So it doesn't necessarily follow strict significant figure rules when you're just simply doing a conversion, temperature to temperature conversion. The reason for that is some people use a fraction, some people use 1.8, 1.80. There's a lot of variations in terms of what you could use. So that is the general rule. If you're converting a temperature that say went to 1 decimal place, then when you convert it, you should take your answer to 1 decimal place. If it was a whole number, take it to a whole number, 2 decimal places, whatever it may be. So if you needed to go from Fahrenheit to Kelvin, you got to go Fahrenheit to Celsius, Celsius to Kelvin, right? And kind of do all those transfers. So technically speaking, these are the, I guess, 4, but they're really 2 because you get the other ones from it. Temperature equations that you do need to know. And I would say out of all these, probably definitely this one is the one that you'll use the most. This one probably second, and these probably won't see too much of these along the way. Any questions on temperature conversions? Again, they will not be provided for you, so you do need to know how to convert temperature values. Yeah. All right, so let's see, we got temperature there. So let's talk a little bit more about conversions, conversion factors, equalities, and dimensional analysis and problem solving and how to properly do that. So first off, as we talked about before, we do have equalities. And again, equalities are things that, again, represent two different sort of units, but represents the same amount of something. And again, if we had 100 pennies, that is the same as $1. And again, that would be our equality. And again, from that, as I mentioned, you could write two conversion factors, 100 pennies over $1, or $1 obviously over 100 pennies. This case, right? So if you had something like 525 pennies and you wanted to figure out, how many dollars that is, you would want to set it up using dimensional analysis. And when we do problems in chemistry, pretty much most of the work should be done using dimensional analysis. Analysis. And that's basically a way where we basically start with a particular unit and we use these conversion factors to get rid of the unit we don't want and end up with the unit that we are looking for. So what we're doing here in terms of math is we are multiplying what's on top and we're dividing by whatever there is on the bottom. So in this case, basically what we're doing is we're taking unit A divided by unit A, and that basically equals 1, or they cancel each other out. It's the same thing as if you took 2 divided by 2 equals 1. They basically cancel each other out. So these units would cancel out, and we would end up in this case with unit B. The easy thing about dimensional analysis is it's basically opposites cancel. So whatever unit you want to get rid of, you put the same unit in the opposite location. So if it's up on top, the same unit goes on the bottom, they cancel each other out. The unit's on the bottom, you put the other guy up on top, the same unit, and it will cancel each other out. The nice thing about dimensional analysis, besides the fact that that is the way you're supposed to show your work in chemistry, not just random numbers on a page and weird calculations, is it oftentimes will help you, frankly, not have to worry about too many equations, because a lot of problems you could just look at the units you want to get rid of and the units you want to end with, and you could just kind of set it up that way and actually, kind of get to the calculation without having maybe use a formula and stuff like that. So for example, here in this very kind of straightforward one here, we would take our 525, we weren't going with pennies there first, I think. And in this case, we want to have pennies in the opposite location, although this is not written as a fraction. Basically, pennies are up on top, right? It's over 1, basically. So that means that we would use our 100 pennies down here and our $1 over here, and our pennies would cancel each other out. We would take basically 525 and divide it by 100, and that will give us $5.25 in this case as our answer. Now, when we do this, this guy here is a conversion factor and is what is sometimes referred to as an exact number. And that means in terms of significant figures, we would default back to this number here, which is 3 significant figures. And that is how many significant figures our answer should have. Now, what is the deal with exact numbers? Where we basically have 2 types of numbers. We have measured numbers, which is like what we were doing earlier, where we have significant figures, and we have exact numbers. And exact numbers are basically found one of 2 ways. They are definitions, or they are basically things that we count. So for example, if I had 3 pens on the table, I'm not going to do some type of experiment to figure out how many pens I have. I'm just going to simply count how many pens I have. So anything that is something that's counted, anything that's a definition, like we just saw there, 100 pennies equals $1, 12 inches equals 1 foot, 1 inch is 2.54 centimeters exactly. These are all considered exact numbers. And the sort of good thing about exact numbers is this: they really could have as many significant figures as you like. And the reason for that is because they could have so many significant figures, or as many as you want to put on them, when we do calculations that involve significant figures, that involve exact numbers, you do not have to worry about them in terms of your answer. So you can basically just ignore them in your calculation in terms of significant figures, and you don't have to take them into account when you're trying to figure out how far you should take your answer to. So you basically ignore them in the calculations, you use them, but in terms of significant figures and stuff like that, you ignore them. Now, there are some exceptions, and just so we're clear, earlier we talked about the 2 different types of units, which are English and metric, basically. So if you're using a conversion factor, which basically came from a English to English conversion, that's going to be definitely considered an exact number. Like 12 inches is equal 1 foot. That's going to be considered an exact number. You won't have to worry about that conversion in your calculation in terms of how many significant figures you should have. If you roll metric to metric, like they're in 1 centimeter, there's 10 to the minus 2 meters. That is also going to be considered an exact number. It is really only when you cross over English to metric that you really should take into account the significant figures in that conversion. There are some exceptions. This is probably the major exception that you find, and that is English to metric there. But 1 inch is exactly 2.54 centimeters as an exact measurement. So that would still be considered an exact number. If you did something like, I don't know, a quart is equal to 946 milliliters. That is sort of an English to metric sort of conversion. And in this case, when you look at this and you write your two conversion factors, you would look at the one that is not 1. So the one that's actually a number here. So you would use that, and that would technically have 3 significant figures if you had that as part of your calculation. And you would have to take that into account for any answer that you got. I would say in most cases, still probably the first number that you start with usually is like the right number of significant figures for your answer, not 100% of the time, but pretty close. But if you do cross over that English to metric, you technically should look at the significant figures. Like if you rounded the 1 pound is equal to 454 grams, that technically would not be an exact conversion. This would then be carrying 3 significant figures when I would use it in a calculation, and you should take that into account. Any questions on that there? So speaking of that, when we do conversions, we do want to think about a pathway to get you to maybe wherever you want to go. So let's just say we had 52 gallons and we wanted to know, how many milliliters that was, right? So we could think about ways to get there, and there are different ways depending on what conversions you might choose to kind of get you in that direction. For example, 1 gallon is 4 quarts, right? And a quart is, as we just saw there, 946 milliliters. So these are 2 ways or way that we could get there. We could go from gallons to quarts using the first equality here. We can then take it from quarts to milliliters using this second equality here. Now, for each of these equalities, once again, you can write 2 conversion factors for each of them. And again, the conversion factors are really just fractions where each of the units go up on top and bottom. And for the bottom one, you could write these 2 here. So when we would start this calculation, we would start with what is given to us. And again, here, we just want to get rid of those units of gallons. So once again, it is on top. So we would want to use a conversion factor here on the right that will take us and get rid of gallons. So 1 gallon on the bottom would give us 4 quarts. If I laid up the calculation right at this point, gallons would cancel and I would be in units of quarts. Now, I'm not really interested in quarts. I do want to get to milliliters. You could do 1 of 2 things at this point. You obviously could get an answer. If you were to get an answer at this point, you definitely don't want to round too much. You want to, again, not round to the very end. Or you could continue on with the calculation. And this is why dimensional analysis should be used, because you could clearly see that quarts are up on top, which means if I want to get rid of them, I need to go opposite again and put the quarts on the bottom. So that would be the conversion factor that I would want to use. 1 quart would go on the bottom, 946 milliliters would go up on top, quarts would cancel. That is going to leave me the unit that I'm looking for, which is milliliters, up on top. If you are solving for 1 unit, in a sense, an answer that has just 1 unit, those units should always be up on top, right? They should never be on the bottom. if my unit was up on the bottom, right, like on the bottom and not on the top here at the end, that is basically 1 over that unit, right, which is the inverse of it, right? So you will not have the right answer. So if you're solving for something, your unit that you're looking to end with should always end up on top by itself, and that will give you the right one. Once again here, mathematically, what we are doing is multiplying whatever is on top, and then we're going to come back and divide by whatever is on the bottom is essentially what we're doing here. And in this case, we would take 52 times 4 times a 946. And by the way, there's not much on the bottom. They're all ones. You would come back and divide by 1 if you really wanted to, but you do not need to, obviously, in this case. And this would give me my milliliter. Now, a couple of things before we clean this up. When you have a calculation like this and you have multiple numbers up on top and you actually have real numbers on the bottom that you might need to put into your calculator, people also screw up this type of calculation by trying to put everything into their calculator all at once. And if you don't do that with proper parentheses, you're going to get the wrong number. My recommendation would be this, and again, not in this example since we don't really have much to divide by on the bottom, but if we did have numbers on the bottom to divide by, what you would want to do is you can multiply as many numbers as you want up on top. At the end, you should just hit equals. And then you should hit the divide button and divide it by the first number on the bottom, and then you should hit equals. Then you should divide it by the next number on the bottom, and then hit equals. And you'll always get the right answer if you punch it in that way. If you try to punch it in all at once, you're going to most likely get the wrong answer because most people just really don't put parentheses in the right spots or don't even use parentheses. And your calculator thinks you're trying to do something that you're not. So that's a very common calculation error that people make when they're doing like a long calculation, got a lot of numbers on top. They got to multiply and divide. Sometimes it's better to keep hitting the equal button and you'll always kind of get the right answer at the end. Now, with that being said, we do want to look at significant figures here. Clearly, also, when you're doing dimensional analysis like this, there's really only 2 types of calculations that you're doing. You're multiplying on top, you're dividing by the bottom, which means you're only multiplying and dividing, which means you should always be looking at significant figures here when you're looking for your answer. So when we look at significant figures, we have our original number here, which has 2. This would be considered an exact number, as is both English. Here, this, we would have to actually look at it, and this would be 3 significant figures, which means still in this case, our answer should end up at 2 significant figures, yeah? And that means that we should go here, and again, you have an option, since that's a 6, you could round this to 2, 0, 0, 0. How many zeros there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 milliliters. The problem with doing that is how many significant figures do I have? I only have 1, right? There's no way that you're going to be able to get that guy into 2 significant figures because we don't want to just get rid of these zeros and put a decimal because now that's 20, and that obviously is not the same value, right? So we don't want to do any extreme rounding. So we would want to go 1, 2, 3, 4, 5 places here and do a little 2 times 10 to the 5 milliliters. And that again will give us our 2 significant figures that we need, still maintaining the value of that number without changing it. Question on that there. Now, why don't you try one? Let's say we had something like, I don't know, let's say we're doing this. Let's say we are driving a nice, respectable 76.5 miles per hour. How fast are we going in kilometers per second? Why don't you take a moment? I'm going to give you some things that might be helpful. There are 5,280 feet in a mile, right? And kilometers. And actually we'll do this one. This might be a quicker one. We'll do 1 kilometer is 0.621 miles. That'll work. And hopefully you know the other conversions from hours to seconds, I hope, yeah. All right, so get what you like there. There are a few different ways, obviously, you could do it. So choose whichever way you want to go. And there are different ways you could get to the same answer. And it really doesn't matter which way you choose, as long as you choose a legitimate way to get there. First off, when we do have like 2 units, like something per something, like miles per hour, that is basically a fraction. And basically what that means is we basically have 76.5 miles over an hour, right? So basically in 1 hour, we're going to travel 76.5 miles is basically what that means. So we actually have 2 units here, and we actually do want to change both of these units, one into kilometers, right, and one into seconds. And again, it's important to set this up with dimensional analysis so you can see where the units are. So if you do this, you could take 76.5 miles over an hour. And typically speaking, the number stays with the first unit and the bottom unit is usually 1. And I'm going to start with the miles, and I want to get my miles into kilometers. And one of the conversions I gave you will directly do that for you, one of those equalities. And again, we want to go opposite here. So miles are up on top, which means we do want to put miles on the bottom so that they cancel. And up there is going to be our kilometers. If I stop the calculation right at this point, the units I'm left with are kilometers on top, hours on the bottom. Yeah. Once again, you could get an answer at this point. I wouldn't round too much, or you can continue on with the calculation. I'm going to continue on with the calculation. And again, the reason we want to set these things up with dimensional analysis like this is now I could clearly see that my hours are on the bottom, which means to get rid of hours, I need to put it on top. And you could do that a couple different ways. You could do hopefully maybe that 1 hour is 3,600 seconds. Or you could do, right? There are how many seconds in a minute? 60. How many minutes in an hour? 60. How many hours in a day? 24, not 60. Yeah. So sometimes people mess that up. So that will not be provided for you. There are some things that hopefully you should know, I hope. Yes. Although I did have somebody once say I couldn't answer a question because you didn't tell me how many seconds were in a minute. But those are hopefully some things that you should know. You could also, again, do the conversion here. Alternatively, you could have went hour to minutes, minutes to seconds if you wanted to do that as well. In this case, our kilometers up on top are not going to cancel. Wrong one. That's going to be our hours on the bottom there. Throw that one there. Hours on the bottom and hours up on top are going to count. So we're going to be left with kilometers on top per second, which is what we're looking for. Once again, we're going to multiply whatever's on top and get hit equals, come back and divide here. And this is sort of what I was talking about previously. I would go 76.5. You don't really have to multiply it by 1, but if you did, yeah. It would not. So this is really the seconds need to be on the bottom because we're looking for kilometers per second. So we want to end up with seconds on the bottom. And again, this is really why you do want to set it up like this, because I can't tell you how many people here would do the opposite and do like this 3,600 on top or 60 and 60 up on top. And that's because they don't really know where the unit of hours are. Is it on top? Is it on the bottom? So this is why you do want to set it up like this as like a fraction and just keep it really simple, top and bottom, right? And opposites cancel. And like I said before, there's a lot of problems later on where you would technically be using a formula, but you could actually just set it up like this. And like I said, get rid of the units you don't want, get to the units you do want, and you'll end up with the right answer without even having to rearrange formulas and stuff like that. So it's really critical that you do set it up like this. I would say a lot of people will do the reverse sort of it and not know like where things should be. So in this case, we would do 76.5. We would times it by 1, times it by 1, hit equals. We were going to divide it by 0.621, which is the first number on the bottom, hit equals. Divided by 3,600, hit equals. And that will give you something like 0.034219002 on your calculator. Again, the units here would be kilometers per second. Clearly, we need to clean it up a little bit here along the way. This is an exact number, right? So we don't have to worry about that. What about this one? Kilometers to miles. Perhaps do you need to worry about that, right? Because that is a metric to English conversion. That's 3. This guy is 3, which means we should end up at 3, which is right here, which means we should end up at 0.0342, again, kilometers per second in this particular case. Any questions on that one? Now, as you can see, I put a bunch of other conversions up here, qualities, and you could use those and it will get you there. It might just take a little more steps. So let's just say I grabbed a couple of different conversions, like miles per hour. We'll start the same. And let's just say I rolled with my 1 mile is 5,280 feet. That would cancel out, and that would give me feet per hour. I then could go in a foot, there is 12 inches. Feet will cancel. That leaves me inches per hour. 1 inch is 2.54 centimeters. An inch will cancel. We want to make sure we do our conversion here right. 1 centimeter is 10 to the minus 2 meters. Centimeters will cancel. And 10 to the 3 meters there is going to be a kilometer. Meters will cancel. And lastly, I could then do my 1 hour is 3,600 seconds. A little longer of a path, but again, should still get you there. 76.5 times 5280 times 12 times 2.54 times 10 to the minus 2, which again is 1 times 10 to the minus 2 if you want to punch into your calculator that way. All divided by a little 3,600 and a 10 to the 3. Gets you your exact same number there of 0.0342 kilometers per second. So even a longer journey, but still gets you to the end. And that does happen with conversions. It just depends sort of which pathway you choose, which conversions you get there. Some are a little bit quicker, some a little further. But again, if they are legitimate equalities, they will all get you there as long as you keep everything canceling out correctly. Any questions on that there? Now, again, you do need to show your work this way with the units, with the dimensional analysis, not just sort of the stacking version of calculations. I like to call it like this, divided by this, divided by this. Before you know, you're not sure if you're dividing, multiplying, where the units are, and people will always sort of mess it up. Yeah. Yeah, I don't care for that. Some people call it the railroad method, right? They're like railroad tracks or whatever it is. You could do that, but it does just need to be, where you see the conversion factors that are used with the units, and that you can kind of see the units canceling out. So it's fine. Yeah. Other questions? Okay. A couple other things about conversions and doing these sort of conversions things that sometimes people mess up on. Let's talk about let's talk about if we had like a prefix to prefix sort of conversion, right? So let's just say we're doing let's just say we're doing 62.5 kilometers, and we want to know how many centimeters that would be, for example. So a lot of people will sometimes try to figure out, I'm going to move some decimals. I see fingers moving back there, like how many places, should I move the decimal and stuff like that, prefix to prefix. Again, you do need to show your work in this class, which means you do need to do it in a dimensional analysis with the conversion factors. So the best thing I could recommend is it is probably the best approach to basically go back to the base unit first and then take it to the next prefix. So the base unit in each of these are meters, right? Kilometers and centimeters. So that really is where you should go with your conversion, and then take it back to the next prefix unit. The reason I say that is you could probably very easily find a table where you could look up kilo and it says 10 to the 3, and you could look up centi, it says 10 to the minus 2. And those are conversions that you could find pretty easily in a table without trying to find the conversion of what's directly from kilo to centi. Remember, you will not have the advantage of your phone or Googling it, right? So you do need to know how to do it. So you can find these sort of conversions really easily in a table. So that would be the approach that I would take. I would start with my 62.5 kilometers. And remember, when we see something like kilo, what that means is in one of the prefix units, which is kilometers, there are 10 to the 3 of the base unit, which is meters. And that, again, is the proper way to use that 10 to the 3, which, once again, if you need to punch into your calculator, is 1 times 10 to the 3 in scientific notation. If you have the calculator with like the EE button, you could probably just hit EE and 3, and you don't have to worry about the 1, or you can put the 1 in there. But that's basically what it represents. This will give us our two conversion factors of 1 kilometer over 10 to the 3 meters, are 10 to the 3 meters over 1 kilometer. So again, here we're going to take the opposite approach. Kilometers are basically up on top. So to get rid of them, we want to go with it on the bottom. So 1 kilometers is 10 to the 3 meters. That is basically going to take us to the base unit, which is in the middle. And that is good because now I know when I look at that table for centi, that 1 centimeter is 10 to the minus 2 meters. So now I have the conversion that I need to go the rest of the way here. And that is what I'm going to use. Once again, that will give you two conversion factors that look something like this, are that. And again, meters are up on top. So we're going to set this up like this so we can see that. We're going to go with the conversion factor here on the left. That's going to put the meters in the opposite location. So 10 to the minus 2 meters is 1 centimeter. Meters will cancel. Again, when we're punching this into our calculators, that is 62.5 times 10 to the 3, or 1 times 10 to the 3. Again, use scientific notation properly. We're going to then hit equals and divide it by 1 times 10 to the minus 2. And that's going to give us something like 625, 1, 2, 3, 4 centimeters. By the way, significant figure-wise, it should have how many? And that's what I have here, right? That's why I didn't put any decimal place. You could also scientific notation that up if you like as well. Again, it'll be 6.25 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 centimeters. So whenever you're kind of going prefix to prefix, I would highly recommend you kind of use that base unit as the middle point, because you could, again, find those kind of conversions really easily in the table and really be able to kind of go from one to the next. Lots of people screw it up by, again, just trying to figure out how many sort of decimal places to move. And besides that, you do need to show your work. So you got to show it that way anyway. So you might as well do it that way. Any questions on that there? All right. So why don't you just do this one here? Let's say we had 3, 5, 5, 5, 5. Why not? Let's go with cubic centimeters. How many cubic feet is that? So there are 12 inches in a foot, and there are 1 inch is 2.54 centimeters. Why don't you give that a go, see what you come up. Okay, so let's take a look. First off, this is what type of unit? What does it represent? Cubic centimeters, is it like a length, a volume? It is a volume, right? So that is actually a volume. These are all length measurements, right? And we get a volume measurement like that by taking something like the length times the width times the height. And if you measure them all in, say, length measurements of centimeters, that gives you a cubic centimeter, which is a volume. Yeah. So basically, if you take the length measurements, 3 of them, and multiply them together, length times width times height, oftentimes it's used to find like the volume of a cube or something like that, right? Will give you a volume and stuff like that. So it's really important to know that. And by the way, this particular one 1 cubic centimeter is the same as a milliliter, right? They are a 1-to-1 sort of conversion. And in medicine, they sometimes use a cubic centimeter as a cc, like give that guy 5 cc's before he dies, right? So that's a cubic centimeter. So if you look at a syringe, that's what they are in, or like an IV or a syringe or something like that, or cubic centimeters. So these are all volumes, and that's commonly used in chemistry, these two versions of it. Speaking of volumes, right? 1,000 milliliters, by the way, is equal to 1 liter. That's also a very common volume conversion that's used a lot. So in this case, we could use these length measurements to kind of convert these guys out. So when we go to do this problem here, we got 35555 cubic centimeters. We do want to get rid of the cubic centimeters, which means we can go this route first. And we will go 2.54 centimeters is 1 inch in this case. By the way, if I do just that, did I convert it to cubic inches? I did not, right? You actually have to do this conversion not once, not twice, but technically speaking, 3 times you need to do this conversion. 1 centimeter, 2 centimeters, 3 centimeters is a cubic centimeter, which completely cancels out the cubic centimeters that we started with. And up on top, we now have inches times inches times inches, which actually turns our top right at this point into cubic inches in terms of the units. Yeah. Now, because that's cubic inches, we could then use our inches to feet here. And again, we could see from our dimensional analysis that inches are up on top, which means they do need to go on the bottom. 12 inches is 1 foot. Once again, we actually have to do this 3 times to properly get it to cancel out. 1 inch, 2 inches, 3 inches is cubic inches, takes care of 1, 2, and 3 inches, leaves us up on top feet times feet times feet, which gives us our cubic feet that we're looking for. At this point, we're basically taking our original number, since everything else on top is 1, and we're going to divide it by 2.54, hit equals, divided by 2.54, hit equals. 2.54 hit equals, divided by 12 equals, divided by 12 equals, and divided by 12 hit equals. Will give you 1.2556. And this would then be cubic feet. In terms of my significant figures, these are all exact numbers. These are all exact numbers, which means I have to default back to this guy, which is actually 5 significant figures in this case, and you will end up with that answer. Now, the question may be, could you not just do it like this, or write the number correctly first? Would be good to start with. That's right, 2, 4, yep. And that is cubic centimeters. Could you not just go 2.54 centimeters is 1 inch, put a little cube, and 1 foot is 12 inches, and do a little cube? The answer is you absolutely can do that. But in my experience, when people do it that way, they cube the units, but never live to actually do the numbers. And they just do the numbers once because they can't visually see that you should do it like 3 times. So if you don't want to screw it up, I might do it individually like I did there on the bottom. If you're careful, you could definitely do it on top, but very common mistake. People will never do the number. They'll just do the units, and they'll just end up dividing by 2.54 once and 12 once and wonder why they got the wrong answer, because they didn't actually cube the number, the part in there. Any questions on that? So that's, again, a very common thing. You got to make sure, that you get rid of the units, all the units, and not just do it once. Any questions on that type of conversion? Question on conversions, equalities, dimensional analysis, how to set it up. This is what it should look like, yes, when you do problems. All right, then we're going to roll into, why not density? Seems like a good one. So density is the relationship of mass of a substance to its volume. And that is actually the equation. Density is equal to mass divided by volume. And you can think of this as a formula, obviously, and can rearrange it. If you want volume, that is the mass divided by the density. And if you want mass, that is volume times density. Some people learn perhaps the classic DMV triangle, maybe. Yeah. Density is mass over volume. Volume is mass over density. Mass is density times volume. Typical units of density are grams per milliliter, are grams per cubic centimeter for solids and liquids. And again, as we just talked about a second ago, a milliliter is the same as a cubic centimeter. For gases, as we'll see when we get to the gas chapter, a lot of times gases density are given in grams per liter rather than grams per milliliter. But most of the time, density is sort of given in these sort of units here. So when we talk about density, if something is more dense than water, for example, it will sink in water. And if it's less dense, right, than water, it will float. Typically speaking, if you need the value of the density of liquid water, it is usually 1 gram per milliliter is typically the value that you use. Density values actually do change with temperature. And so depending on the temperature, the density value will change. But in general, if ever you need really the density of liquid water and it's not given to you, usually 1 gram per milliliter is a pretty safe value to use, but it does change with it. Most things are more dense in a solid state, right, than its liquid state. The major exception is our friend water. Yeah. And that is because when we have something like ice cubes, right, and we put it in our soda, ice cubes end up floating up on top, right? Because they are less dense actually than the liquid water that's in there. And that is an unusual sort of characteristic because what happens, say, with something like water is because it hydrogen bonds with each other. This is more negative, this is more positive. They do a little bonding. And what happens in ice is because of this hydrogen bonding, it creates a lot of open space between the different water molecules. When they lose energy, they just can't close in on each other because of that really strong hydrogen bonding. It creates a lot of empty space within the ice molecules. And what that does, if you think about density, is it creates a larger volume, right? Because there's a lot of empty space now making up more volume. And since density is mass over volume, volume will be larger on the bottom, giving you a smaller density value. Then in the liquid form with water, it has a little bit more energy. So they're actually able to kind of get in closer to each other, the water molecules. It doesn't create as big of an open space between the water molecules. And that's why liquid water actually has a higher density than ice, and that's why ice floats in water because of that lower density. That's also really good for ocean life or water life, right? Because things like lakes and stuff, right? They freeze from the top down, right? Cold ice floats to the top, doesn't allow the bottom water to freeze, so all the fishes are okay, they swim around. If it was the opposite, right, it froze from the bottom down, that would not be good for underwater life, right? Because everything would be frozen at that point. So it actually has some benefits, right? Also, if you want a party trick, right, you take a can of like Diet Coke, a can of regular Coke, you put it into a thing of water. Will they both sink? Will they both float? The answer is one will sink, one will float. Which one will sink? It is the regular Coke because it has a lot more sugar, right? So the Diet Coke has artificial sweetener, not as much sugar, so it's actually lighter and it'll actually float. So you'll have like a floating can. Good for the 4th of July picnics coming up. You look in the ice cooler and everything's melted and all the Diet cans are floating. The solid guys are there on the bottom. So when we talk about density, there's really the volume part of it. There's kind of 3 ways that we could get the volume in a density sort of problem. One way is very simply, we could just, like we talked about earlier, you could just simply read the meniscus and obviously take a reading of the volume. The other way is obviously if you did like the length times the width times the height, Again, if you had some type of cube that you were measuring, you could get the volume of that cube. And again, as we talked about, if you did them all, say in centimeters, for example, you don't have to, but you could do them all in centimeters. That would give you something like a cubic volume, a cubic centimeters, which is a volume. The other common way that we get a volume, especially with density, is volume by displacement. And that means that, for example, if we have like a graduated cylinder here full of some water here to start with, and we have an initial volume reading, and we take some type of solid object and we drop it into, say, the graduated cylinder, what's going to happen is your volume level here will increase as the solid will displace the volume liquid. And it will displace a volume equal to its own volume. So if you take the difference between the final volume minus the initial volume, that will typically give you your volume of your object. And that again is a way that we can very easily calculate the volume of a solid object. Just drop, and that will give you the volume. Now, when we have the density of an object, like the density is 2.65 grams per milliliter, and we wanted to know, for example, how many milliliters would, say, 525 grams of a metal represent or something like that. We could actually use the density as a conversion factor. And this is what I was talking about a little bit earlier. So for example, here, I'll just roll it over here, 2.65 grams per milliliter. And we have a mass of, say, whatever I had there, 525. I'll just make a new number up. And so obviously this is going to be a density problem, and you could roll out your density equation here. And obviously we have the density given to us. We have the mass given to us. So we want to solve for the volume. The volume here would be mass divided by density by rearranging it. And you can plug and chug into this equation. So what I was saying earlier, where you could kind of, and you set it up with dimensional analysis, you really don't even have to think about the equation, is, for example, a situation like this. You could take the density, which has 2 units, and typically if you're given any type of value that has 2 units, you could basically write 2 conversion factors for it and just treat it like a conversion factor. And you could do it in the opposite direction. So now if I wanted to figure out, how many, say, milliliters there was of this, I could just take my number here, that is the single unit, and use this as a conversion factor and go, okay, that is what I need. That is the opposite direction. And now those will cancel. And what I know is in dimensional analysis, I always multiply the top and divide the bottom, which means I am going to do the correct math here, which is division, which is when I rearrange it. And I didn't even have to think about the formula here. I just did a dimensional analysis, got the units I want away, kept the units I need, and I didn't even have to worry about the formula here. And I now can do this calculation correctly. And again, without even having to remembering the formula in a lot of cases. That gives us something like 198 milliliters in this particular case. So this again is the benefit of sort of doing problems in dimensional analysis, kind of doing that unit cancellation. A lot of times you don't even have to really worry about the sort of formula and rearranging it correctly, because it'll kind of take care of it itself by just going opposites and cancel out the units you don't want and keeping the units that you do want. Any questions on that there? All right, so I think, if I'm not mistaken, that should cover